Hello ladies and gentlemen. What we are going to be discussing in this video lesson is how you solve exponential equations. Now this is something that anybody that has taken a second semester of Algebra 2 has seen at some point, because that's typically where you see it, more towards maybe the middle or closer to the end of the second semester, but that's typically where you see it. Now, solving an exponential equation can be relatively simple, but it could also be relatively difficult depending on how the equation is set up. Now, by and large, at its most basic level, what you need to do in order to be able to set up and solve an exponential equation is the base of the exponent on the left side of the equal sign and the base of the exponent on the right side of the equal sign have to be the same. Whatever that number is, it has to be the same. So whatever we have as the base, it has to be the same. It doesn't make a difference what number it is. The base has to be the same. Once the base is, and I know I'm repeating myself a lot, but you get the idea. Once the base is the same, whatever that number is, 5 and 5, 3 and 3, whatever, the bases don't matter anymore. And I just set the exponents equal to each other, and then I solve for whatever my variable happens to be. And then once I have my variable, the solution to my variable, we can go back and check to see is it the correct answer. Now, as a quick refresher, here there are some properties of exponents that we need to make sure that we recall. So here are the 6 basic properties of exponents. So this one would be called, this is the product of powers, meaning that when the bases are the same, you add the exponents. This one is the power of a product, meaning that if I have bases that are different, but they're multiplied, and whatever that product is raised to a power, I can separate it and put the exponent with each individual base. Here, we would just think of this as the, oops, I can't spell, negative exponent rule. Negative exponent rule. And what that tells us is that we don't like negative exponents. We really can't have a negative exponent. So whenever I have a negative exponent, I take the reciprocal of whatever the base is, and by doing so, I can change the sign of the exponent from a negative sign to a positive sign. And it works that way if I start off with a fraction that's negative. I can take the reciprocal of it, put it in the numerator, and make it positive that way. On the right side here, we would call this the power of a power. And all of these are rules. So basically, in the parentheses, we have a that's already raised to some power that's typically something other than 1. So like a squared. And then that is being raised to some other power. We could say like 3. Well, whatever those two exponent values are, we can multiply those together and write it as one new number. So like in the hypothetical that I'm giving you, we would say a to the 6th power. Here, a to the 0, this is just called the 0 exponent rule. Now I can explain this to you in further detail in class if you would like to. So if you need to, or if you want me to explain this further in class, please make sure you ask about it. But essentially, anything that's raised to the 0 power is simply the number 1. And the last one that we have here on the right is the quotient of powers rule. This is essentially the reverse of the first one that we had, the product of powers. Product of powers says that if the base is the same, and I'm multiplying powers with the same base, we just add the exponents. Well, the opposite is true here, is if I'm dividing powers that have the same base, we can subtract the exponents from each other. So there is the quick kind of review of uh, rules of exponents. So here are our first two examples. So on the left side of so I'm looking at the equation on the left first, and on the left side, the base is 2, and on the right side, the base is 16. So clearly the bases are not the same. Now 2 is a much smaller number than 16. I can't simplify 2 anymore and keep it as a whole number because it's a prime number. But 16, on the other hand, can be simplified. What I want to do is I want to try and see, can I simplify the base of 16 to have a base of 2? Now I'm going to use kind of like my synthetic division notation here, and I'm going to just divide. So 16 divided by 2 is 8. And if I divide that by 2 again, that'll give me 4. And if I divide that by 2, that gives me a 2. And if I divide that by 2, that gives me 1. So it takes 4 2's to make 16. So that tells me that 2 to the fourth power is the same thing as 16. So I can rewrite 16 to be 2 to the fourth power. Now, at this point, the bases are the same. So because the bases are the same, we no longer need to write the bases, and we can take the exponents themselves, on the left 2x minus 2, and on the right 4, and set them equal to each other, and then solve it like any other normal equation. Move the 2 over from the left side to the right side through addition, and I get 2x is equal to 6. Divide both sides by 2, and in this case, x will equal 3. So now let's check it. Did we get everything correct? So I'm going to take my answer, and I'm going to substitute it into the original problem. So I have 2 to the 2 times 3 minus 2 power being equal to 16. So if I say 2 times 3, well, that's 6, and 6 minus 2, that gives me 2 to the fourth power equals 16. And this is where we might want to check ourselves on a calculator and just say, is 2 to the fourth power 16? So if we say 2 to the fourth power on our calculator, we do get 16 to be equal to 16. So we know that x has to equal 3 for our answer in this case. So let's look at the problem on the right. So here I have a base of 25, and on the right I have a base of 125. Neither of those numbers is a prime number. They can both be simplified further. I'm not saying that every time we try and simplify a base, we're going to simplify it to be a prime number, but those are a good number in which to try and work with. So on the right side, a prime number that is a factor of 25 is the number 5. And I don't think I really need to do this one to demonstrate, but I will. 25 goes into, or 5 goes into 25 5 times, and then 5 goes into 5 1 time. So that means 5 squared is essentially the same thing as 25. So now I'm going to do the same thing with 125. See how many times 5 goes into 125. Well, 5 goes into 125 25 times, and I can continue breaking that down to see how many times I would have to raise 5 to equal 125. So here, 5 goes into 25 5 times, and then 5 goes into 5 1 time. So that tells me that it's going to say 5 to the third power to equal 125. So now that we've identified that 5 is a common base between both the left side of the equal sign and the right side of the equal sign, and what value we would have to raise 5 to in order to equal uh, the 25 or the 5, we can rewrite the equation as 5 squared to the negative 2x power being equal to 5 cubed to the x plus 7 power. Now this is where we need to look back to our rules of exponents. Both of these are a power to a power. So what we're really going to wind up doing is taking the exponent that's inside of the parentheses and multiplying it to what we have outside of the parentheses. So this becomes 5 to the negative 4x power equals 5 to the 3x plus 21 power. And at this point, we've established that the bases are the same, so now we no longer need to write them. We take each exponent, set it equal to the other one, and then solve like normal. Here in this case, since negative 4x is by itself, I'm going to take the 3x from the right side, move it to the left side. So I'm going to subtract both sides by 3x, and that's going to give me negative 7x to be equal to 21. Divide both sides by 7, or negative 7 in this case, and x in this case will equal a negative 3. So here is the solution to the problem, and let's do a quick check on that one just to make sure. So let's check that one. If I say 25 to the negative 2 times negative 3 power equals 125 to the negative 3 plus 7 power, well, this is going to give me 25 to the 6 power is equal to 125 to the 4th power, and this is where we need a calculator. So if we type this into our calculator, 25 to the 6th power is going to be 244,140,625, and on the right side, again, we use the calculator. 125 to the 4th power will also equal 244,140,625. So it checks out both on the left side and the right side of the equal sign. So let's try a couple more quick examples, and particularly I want to pay attention to the fact that on one of them we have a fraction for our base instead of a whole number. So here, again, this particular problem on the left side is just another example that helps us identify what bases could we use besides the ones that are there. On the left side, I have a base of 81 to the 1st power, and on the right side, I have 27 to the x power. So here, 27 is a pretty clear number as far as saying, well, I could divide that by 3. That is a prime number that I could divide 27 by in order to simplify that base. 81 isn't quite as intuitive to say, okay, well, 81 is a multiple of 3. But let's check it. Since I know 3 works for the 27, let's check to see if 81 can be divisible by 3. And if it is, how many times? Because that'll tell us what power we raise it to. 81 divided by 3 is 27, which is a dead giveaway to say, yes, it must work as 3 is a common base, since 27 is the base on the right side. If I divide 27 by 3, that's going to give me 9, and 9 divided by 3 is 3, and obviously 3 divided by 3 is 1. So that means 81, I'm sorry, not 81, but 3 to the 4th power is equal to 81, and since we've already divided the 27 at some point by 3, well, that means that 3 to the 3rd power is the same thing as 27. So I will rewrite the problem as 3 to the 4th power, and since 81 doesn't have any exponents, I don't really need to put that one in parentheses. So I'll just say 3 to the 4th power is equal to 3 to the third power to the x power. So 3 to the fourth power is equal to 3 to the 3x power. When I say the power of a power rule, the exponent of 3 times the x is just 3x. Now that the bases are the same, we can say 4 is equal to 3x, and in this case, divide both sides by 3, and we get x to equal 4/3. And this is where you would just check it on your calculator. If I say 27 to the 4/3 power, it will equal 81. So this one isn't really much to show as far as checking it. You would just put the 27 to the 4/3 power in your calculator and hit enter. So the last example here is 1/2 to the 3x power is equal to 8 to the x minus 2 power. Now this one we could actually kind of do one of two ways, because in the parentheses, the 1 is being raised to the 3x power, and so is the 2. The 2 in the denominator is also being raised to the 3x power. So I could begin by saying 1 to the 3x power over 2 to the 3x power is equal to 8 to the x minus 2 power. Now you could do it this way and see what you wind up getting. And let's go ahead and try working it out and just see how it goes. And if it works, then great. But there's another way that I would like to show you that I think is going to be a little bit easier. But this is a way that I know some students will attempt, so I want to go ahead and try it. So we have 1 to the 3x power over, now I don't really like anything in the denominator in order for me to have it. In fact, the more I think about it, well, 1 to the 3x power, anything raised to the 1 power, well, that's just, or 1 raised to any power, no matter what x is, that's just 1. So let me go ahead and clean this up a little. Oops, go back to my eraser. Let's clean this up a little bit. 1 raised to any power is just 1. Okay? Now the problem is that I'm going to have that fraction of 2 to the 3x power here, being equal to 8 to the x minus 2 power. One way or another, we have to take that denominator, that 2 to the 3x power, we have to get that variable out of the denominator. So the only way that we can do that is by taking the reciprocal of the function, or the reciprocal of the left side, I should say. And if I take the reciprocal of the left side using my rules of exponents, I'm going to get 2 to the negative 3x power over 1, so anything over 1 is just itself, is equal to 8 to the x minus 2 power. Now we can kind of see that on the left side and the right side, we should have a common base of 2. Now 8 will simplify as a number, as a base. We can have 2 to the negative 3x power on the left side, and I can have 2 to the third power to represent 8 to the x minus 2 power here. So now we can say 2 to the negative third x power on the left side is equal to 2 to the 3x minus 6 power on the right side. And now we have a base that is common between both of them. So I can say negative 3x is equal to 3x minus 6 and solve for 6, or solve for x. Move the positive 3x from the right side to the left side through subtraction, and I get negative 6x is equal to 6, and divide to get x by itself. So in this case, x is equal to a negative 1. Oops, made a mistake. I forgot to my negative sign. When I brought down the 6, there is a negative sign here, so x is equal to a positive 1. Now the way that I could have saved myself just a little bit of work is right here. If I don't take the whole fraction to the power, meaning I don't have to write 1 to the 3x power and I don't over 2 to the 3x power, I could have started off by saying in the parentheses, I could just take the reciprocal of 1/2, which would give me 2 to the negative 1 power times 3x. And at this point, again, we can represent 8 as being 2 to the third power to the x minus 2 power. So by taking the reciprocal of the fraction that's already given to us and simplifying at the same time on the right side, the 8 to be a base of 2 to the third power, we can save ourselves just a little bit of work. So in the parentheses on the left side, the negative 1 times the 3x gives me 2 to the negative 3x power. And on the right side, again, I'm going to get 2 to the 3x minus 6 power, which puts us exactly where we were right here. And again, when I solve it, I'll just get x is equal to a positive 1. So that's how we would take care of something if we had a fraction. If we have a fraction, we can simply take the reciprocal of it while it's inside of the parentheses, then raise it to a power. Or I could raise the numerator and the denominator to the power, and then take the reciprocal of it to see what I would need to do in order to put it, get a common base. So the last example that we're going to look at here is when the base is an irrational number. Now e is an irrational number, just like pi is an irrational number. And it is a number that is very common when working with exponential equations, exponential functions, or logarithms. It is a very common base that occurs in financial equations and some other population growth and decay models. So here, we don't have to necessarily worry about getting a common base because every term that we see in this particular equation is e. It is, so we already have a common base. So the only thing that we really need to try and do is just simplify a little bit so we can get our variables under one base on the left side and one base on the right side. So that way we can set the exponents equal to each other. So looking at the equation here, I'm going to get rid of the denominator on the right side by multiplying e to the negative x power on the left side and the right side of the equal sign. Now on the left side, I'm going to wind up, or well, let's take a look at the right side first. The e to the negative x power in the denominator and in the numerator, well, that just simplifies to be 1. And on the right side, we have e to the negative x power times e to the positive x power. Because the bases are the same, we wind up adding the exponents together, which gives me e to the 0 power. So let me just go ahead and rewrite the rest of the problem with what we've changed. So the only thing I'm changing after I multiplied e to the negative x power on both sides is that on the left side of the equal sign, I get e to the 0 power, and on the right side, the e to the negative x in the top and e to the negative x in the bottom. Those just simplified to be 1. So I have e to the x power plus e in the parentheses equals e to the x power plus e to the 3x power. Now, going back to what we saw at the beginning of the presentation, any number raised to the 0 power, well, that's just 1. Now, you don't necessarily have to write the 1 here, but I don't want to skip any steps and confuse anybody and say, well, where did e to the 0 power go? Well, e to the 0 power is just 1, so I'm replacing e to the 0 with the number 1. And of course, if I multiply anything by 1, well, that doesn't change its value. So if I multiply the stuff in the parentheses on the left side of the equal sign, I'm going to just get e to the x plus e equals e to the x plus, e to the 3x. Pardon me. So now, it doesn't matter which one I move. If I take the one on the left or the one on the right, if I subtract e to the x from the left side or the right side, we're going to see that those are going to cancel each other out. So at this point, I'll be left with e to the first power is equal to e to the 3x power. So at this point, now we have one term on the left side and one term on the right side where the bases are the same. So the exponent on the left side of e is just 1, and the exponent of the right side of e is 3x. So I can just set 1 is equal to 3x, divide both sides by 3, and show that in this case, x is 1/3. And this is a difficult one to try and, write the check of to see does it work, because e is not a very nice number to write. But if you did take the time to try and put the 1/3 into all of the exponent spots there, you would see that it would actually produce the same number, but it would be a very funny looking number. So if you have any questions throughout the course of this presentation, again, the main thing that we're trying to do when solving an exponential equation is to get a common base on the left side and the right side in a single term, so that way I can set the exponents equal to each other and then solve for x like normal. And that's about it. So if you have any questions, make sure you have them written down. Bring them to me when you see me in class, and we'll see you guys soon. Thanks.